things about some general wrap-up stuff. But before that, we've got to hear from Arash Nourian. And listen, Arash is someone who's been here at Berkeley now for a couple of years and done stuff at the iSchool, engineering school, here at Haas. And he's going to talk about the data architecture piece. Now remember we talked about data architecture, data architects, and data engineers, and then we talked about data scientists, and then we talked about data-driven decision makers. And we've heard from data-driven decision makers, we've heard from data scientists, but we haven't heard from the people that really make it all possible. The guys who handle all the pipes and the storage and all of that. And Arash is an expert in this topic. And so he's going to step down from all of his advanced, high-level, sophisticated engineering ease and try to translate some basic stuff to us about this very important topic. So welcome Arash.
Thank you. Okay, thanks, Greg. So my name is Arash Nourian. So I'm right now in the faculty at the iSchool. So before I come to Berkeley as a postdoc in computer science, I was working at MIT building the next generation of the big data systems and our pipeline for the data storage and retrieval systems. And then I moved over here to expand one of the frameworks called Spark to be able to be applied on the real-time analytics at the record level, which I go into talk briefly after in my talk. So, so I'm not going to bother you about the 3 V's. So people have been talking about like the volume, velocity, and variety in the past couple of years so far, but I wanted to bring to your attention exactly what these 3V means actually. It's because a lot of people talking about this without knowing that when we're talking about the volume, what do we actually mean when we talk about the large volume? Is that just a gigabyte or terabyte? How many of you know something more than zettabyte? Just raise your hand. So there is something to learn at least in this lecture today. So we see a shift from like an in-house application in the past 10 years from the like ERP and also a CRM application toward the web-based applications. And you see on the y-axis over here, what would be the increase in the amount of data that's going to be basically processed by the application as we move on from in-house to outside world, mainly in the internet. And then when it comes to the big data world, when we talk about like a minimum data storage that is going to be processed by any big data system, we're talking about in the range of terabyte to petabyte. And then this was like the main issue for the companies that were gathering this much of data like in past 6 or 7 years ago. But now the average company, they are also having like in the terabytes data zone right now. They are in that zone already. So that requires like having a system that allow them to basically actually store and be able to process that data efficiently. So, we see that in the average company, there would be a 44 times increase in the amount of data that they're going to store or capture or even be able to process by year 2020, and going from like even nearly 1 zettabyte of data to roughly 35 zettabyte of data. That's going to be basically gathered by medium to large companies in the next couple of years. And we see that there's a shift in the exponential increase in the amount of data that's, like I said, they're going to be generated. So, and companies have to adapt technologies and the architecture that allow them to move from even before terabytes all the way down to at least a zettabyte if they wanted to compete in the modern industry where everything is going to be like based on the data processing. So starting with like Google, Twitter, and Facebook a couple of years ago, the average number of like tweets that are gathered at Twitter every day, I mean the actual physical tweets that you store on disk is roughly about 12 terabyte of tweets. And then, we see at Facebook every day there's a log data meaning that when you log into your Facebook profile or Facebook page, you click something, those kind of things are captured, and it on average generates like roughly about 25 terabyte of data every day. And so imagine that if you wanted to process that in order to extract some insight, to recommend something to the user or analyze some of the trends for a particular day, then that's a challenge. You have to process that data. And if we bring the Internet of Things to the context, even these numbers would be kind of like a funny, or it's really even small in comparison to the amount of data we expect to receive from the all the sensors and the small devices, wearables, and all those kind of things. So, which we already see that by 2014 there was 200 million smart meter installed around the world, and then the amount of RFID tags right now it's reached to roughly about 100 billions. So if they wanted to, if there's a company that wanted to utilize this devices efficiently and then take advantage of all the capabilities that they have in order to reach out to customer more efficiently, so they have to be able to process this amount of data pretty fast. So if we go back to the large collider project, so that generates roughly about 15 petabytes of data every year. And for the scientists to be able to dig into those data and trying to come up with the efficient way of maintaining or even calibrating the collider project, collider device, so that's a challenge. And so some people are asking, what is actually 1 petabyte? We know that the numbers, we wanted to have some sort of a comparison when it comes to understanding what actually 1 petabyte is. So I have a couple of statistics here. So if you wanted to basically download over 4G networks, 27 years of data, so that's roughly equals to 1 petabyte of data, or a capacity to 100 libraries of Congress if you have a chance to visit that.
Does anybody remember what a floppy disk is?
Yeah. Yeah. I have this issue in the computer science department when we're going to teach these concepts. We're going to talk about the tape, and people are asking me, especially young generation, what is tape? Could you show us what that is? But the floppy disk was the minimum unit of storing data when they basically came out for the PC, for the personal computer, where you could basically store in a couple of even single text file or the Word documents, and then you will be basically running out of the storage, and you have to buy more and more, and then you create a stack of lots of this in order to just, for example, store not even a video, but just some snapshot of a video. So, and then that is actually what you see about the 1 petabyte of data. And then in some sense, you think that it's really large, but it's in other sense, if you look at it, it's not that much of a data anymore. So it's kind of like I said, we have passed that era. The petabyte was something like a dream, or a few companies were working in that space. Now, we see that average companies are moving into that direction pretty quickly. If you wanted to be able to, at least 2 microgram of DNAs, basically on disk storage, is roughly equal to 1 petabyte. So if you wanted to do DNA sequencing, if you wanted to be able to process DNA efficiently and fast, you should be able to basically store even more than thousands of terabytes in order to be able to extract some meaningful data from the DNA strands or sequence. Or 1 day of video that are uploaded to YouTube is roughly equal to 1 petabyte. So mostly cat videos, but that is, that's the reality. So if the YouTube wants to come up with some mechanism to do advertising, to do the real-time recommendation to the user based on their search behavior, they should be able to analyze that on a daily basis. And or 200 servers logging at 50 entries per second for 3 years. So the logging, again, so when they capture some information about your browsing history, about your activity with the website, or connection to any service provider, those are all categorized as logs. And then that is also even smaller than 1 petabyte for 200 servers, which is on the low bar for any small to medium data centers around the world. So, and just wanted to give you a sense of when we're talking about a big data processing at a larger scale, what do we mean by the volume even when we pass the petabyte zone. So each jet engine produces 20 terabyte of data per hour. So that's, if you multiply that by 2, obviously, I guess we have 2 engines because of the redundancy issues. So we generate 40 terabyte of data per hour for just 1 jet engine. If you multiply that by the average number of hours that a flight took from Los Angeles to New York, which is 6 hours, multiplied by the number of like the flights in the US, commercial, and in a year, you get this number, like a 2 billion terabyte. So, and in the aviation industry, if they wanted to come up with like a better way of managing the fuel consumption by the airplane and see what's going on or how they can improve the functionality of the airplanes, so being able to process that much data is a challenge. So they cannot fit it into one device or one small box or even a couple of them clustered together. They should adopt some big data architecture in order to be able to handle this data in the first place, let alone to be able to dig into it and then extract some insight from it. So, and then I said we started to passing like this terabyte stuff going to petabyte and even exabyte. And now we're seeing that the big companies like Google has already moved to yottabyte and bruntobyte. So, and then these are the maximum, the geobyte that you see right here is like the amount of data that you could basically eventually handle right now with the current technology. So, and you see that even like the megabyte and gigabyte and terabyte is kind of like a low bar, and in a couple of years ahead, you won't even think about those kind of like storage units anymore. Similar to floppy disk, like in the past 20 years, so they're going to disappear pretty soon. But if you go and then look at what sort of a data Google had to compile and crawl around the web back in 2000. A year when they wanted to build their search engine, they actually use some of those commodity machines, small machines that even right now, the iPhone 7 and that most of the laptop that you're using are much like super faster than the machines that they were using back then. So this is like a shift that you see that you have to also adapt with explosive data that's happening in order to be able to have the competitive edge that they had. So. Even this is like people thinking, oh, okay, so this is like the maximum. So we go to the geobyte, and that's, I said this is like the maximum that you could handle right now. But we have even more, storage units now that people are thinking of, hey, if we pass this geobyte, then what we can do. So these are not like in the order, but you could see that, there is a potential that we can increase even beyond that spectrum if we wanted to be able to come up with the systems that can capture the data even more than what we are able to process even. So the other thing is, which is really important, is the velocity. Now we were talking about that the velocity that the data is coming pretty fast, but there is this misconception that when you're talking about the data that's coming fast, what do you mean? How fast are you talking about? And then this is something that I thought that may be useful to you guys to know that when we're talking about the speed of the data, we're talking about even sub-millisecond per second, sub-millisecond data that is received by a system. They wanted to be able to process that data in that tiny time frame and be able to respond in return within a short period of time with a small latency. And we're talking about the online analytics. So we're talking about the systems that can react in even less than millisecond to some interactions that can be captured from the user and come up with some recommendation. If the user wanted to browse something in Amazon, and if you are not able to process the browsing pattern and then match it with some recommendations that you can give the user within a minute or so, then the user has already been gone to another page browsing for something else, and then the recommendation that you come up with is not even valid anymore. So all the processing that you did before is kind of useless. So you want to be able to do those kind of processing in real time pretty fast. So we have some examples here. The data that's coming from mobile devices are not pretty fast in comparison to the data that we gather from the sensors. And also the sensor networks or the scientific instrument, especially for the wearables. But I wanted to show you that if you couldn't be able to handle velocity and volume at the same time, you may not be able to provide some sort of a competitive advantage or some innovative solution for the customers that are basically looking at your service. So let me just, before I talk about this, let me just show you what I mean by velocity. So, apparently this is, for some reason, is super slow. Just refresh this page. Anyway, you know, here it's, I think it's super slow for some reason because it's have like a low computational power, I guess. But if you load this website on your laptop, Internet Live Stats, you will see the speed of data. You know, it's pretty fast. So we are receiving, like, you know, roughly today so far, it's like 150 billion emails were sent, or like 425 million tweets so far has been sent. So, and when we're talking about the systems that are able to cope with the velocity of data, we're talking about the systems that are able to capture and process data as data arrives to the system, which is a challenging. It's not an easy thing to do. If you go to this website, you should be able to see like the speed of the data as it arrives, and there are a bunch of good stuff here, even some like website hack today. It's like 60,000. And or the amount of CO2 emission even today, even past of 1 million tons. So, second.
Using the mouse?
Yeah. Yeah, that's
you can
okay.
Also do the touch screen.
It's okay. I just wanted to search. So the system should be able to basically cope with this, you know, fast and speed of the data, and be able to process that data as the data arrives. So we don't want it to gather data and come with some insight like a 1 hour later, because that won't be like valid anymore. And I wanted to tell you about what has been changed in the industry over the past couple of years. So the old model was we were generating the data, and then we consume the data later. So we were not interested to basically, you know, process the data as soon as we receive the data. So we get the data, and then we say, okay, so we'll process that. We come up with some insight. We come up with some like metrics, and then we will just react later after we consume that data. And then, so there were few companies that were, or few sources that were generating data, and a lot of people like, you know, consuming that data that were generated by some few other governmental agencies or some big companies, you know, making those data sets public, and the people were using them to do experiments, to do some cool stuff with it. But what has been changed in the past few years is that, you know, everybody's generating that data. So, and then, so this goes from the many-to-one relation, goes to many-to-many relation, where companies also are the consumer of the data that is generated by the people or other companies, or small, even small companies. So systems that are capable of handling data in a large volume, which we refer to as data at rest, and also the velocity, at the same time variety, because like everybody is generating data, and then depending on the devices that they're using or the system that they are deploying, they are generating different type of data. So the system should be able to address these three fundamentals in real time. So it should be able to process a large volume of data, should be able to react in real time to the queries that comes to the system, should be able to handle a variety of data as not just one type, specific type, like a text file or voice. And also, this is like there are tens of other V's as well. So this veracity is really important, meaning that the data, whether the data that we're gathering is right, has the right quality, is correct, it's not corrupted. We can trust on that data, we can react based on the data we receive. That is another challenge, especially with the Internet of Things, when the data is coming from the sensor with low computational resources and the low powers. Sometimes you're not getting the data in a high quality. The data sometimes is corrupted or is not correct, so you have to come up with some mechanism to verifying the correctness of the data in order to be able to react. Think of it as an example like a sensors that are sending some information to the control room, like a SCADA systems, where they monitoring, for example, the oil refineries, the well, and then if the data comes wrong and then you react differently, you may create some catastrophic event. So Now, the traditional solution in the data architecture comes into like this notion of the data warehouse or the ETL system, extract, transfer, load systems, where people were even the relational database like SQL, MySQL, those kind of systems, where you were saying that, hey, I'm going to get this data and store it in a way that I think would be useful for the people to use it. So if I come up with some schema or some structure that I think it's useful, so I try to transform data to that structure that I was thinking is useful. And then I make that available to people so that they can query and then work with that data with the schema that I define. But this created a lot of problems, especially in the big data system where people coming from different domains and they wanted to use the same data differently, and then they had to transfer the data back again to the format that they wanted to use. So this amount of like a transformation after transformation created a lot of delays especially for the real-time application where they wanted to react very fast.
So it's kind of like if I'm creating a table, right? I'm going to put it in alphabetical order if I think that people are going to be, they want to find, they don't know exactly what they're looking for, and so they want to find it by that title.
Right.
Others, they may just want to, if I know ahead of time that they're looking for the most popular things, then I'm going to rank order them in that table from, highest to lowest.
It's not like the order of the data within a table per se. It's like the way you structure it. Like, if there's a table, you have a first name, last name,
sure.
And then the one way is that you put a first name and last name in one column with comma. The other thing is that I'll put first name in one column, last name in another column. So some people, they just wanted to use the last name, not the first name.
So the idea is data architects basically have to think ahead of time about the ways in which the user is going to want to use the material before they can even think about how they're going to structure, how they're going to
exactly. And then that limits the amount of innovation or usability of the data, because you have to think about some of the questions that the people may have in advance, and then you may not basically exhaust the list of questions that the people could have or could use this data. And you structure it narrowly based on your perspective. And then the people later on, they wanted to use the data differently, they have to transfer the data back to another format so that they can use it for their systems. An example of this system is we have most of the relational database systems like Oracle, Teradata, SQL, Microsoft SQL. All of these systems are in these solutions, or the SAS, or even R for the analytics. But what is changing is that the technology has shifted towards the systems that are able to process data in a large volume and also in the real time. So and the data also is generated even more than what we expected. We cannot even fit that data in some of these conventional technologies like Microsoft SQL Server, like a big data system. And the company, they wanted to basically be able to process the data that they capture in different contexts. They don't want it to create like one static schema and then bound to it, because later, at some point of time, if there's a new customer that wanted to use this data differently, so they wanted to be able to answer to those requests in real time. So we have a couple of technologies in this space that are able to handle this kind of use cases. So Hadoop, or like HDFS, is a file system for Hadoop, is a 10-year-old technology, and it was developed with the idea of that, hey, we are not going to basically build a big computer that we can store every data in this. So we're going to use small computer cluster together and then create a big computational power and storage, so that we can basically, by clustering together, so we create a big storage space and also big computational power. But that had like a lot of challenges that need to be solved by just looking at the communication between these machines and trying to make sure that everything is happening correctly. But after this, especially recently, people are really interested in the streaming analytics. That you wanted to be able to process data as they are generated and then react accordingly. But you don't want it to lose that historical analytics capability that comes with a legacy system like Hadoop. You want it to be able to use these two together. An example of this is like in the fraud analytics, where you create some like profile about some malicious transactions, and then you create that profile over like a course of a year, and then you want it to be able to match a transaction that is happening like in a second or so to that historical data in real time, and then decide whether this transaction is malicious or not. So that is one use case for combining these two together. And there's another challenge in this space is object storage or software-defined networks. Amazon and AWS services, they are giving you the cheap storage, even like less than 10 cents for like a gigabyte of data on S3. So you could basically get rid of all the data warehousing that you had to store the data and just use these cloud services to address the cost, keep up with the increase in the volume of data and also the speed of the data. Because if you are going to create your own data centers with the storage and the server, so obviously you have to know in advance the increase of the the growth in the data volume that you're going to store, and also every couple of years there would be a shift in the technology, and especially in the storage space. Then you have to renew and then buy new storage system in order to be able to cope with the speed of the data. Something that you may know or you may not is like in the storage when we're talking about it, like a storage that is able to store like 1 petabyte of data or 1 terabyte of data. There's a whole suite of storage with a different level of speed in terms of reading and writing the data. That's called IOPS, input output per second. So you could get a terabyte drive for like $100. But when you wanted to write to that or read from that, you have to wait like a couple of minutes. Whereas you pay like a few $100 in order to get the same drive, 1 terabyte, but you can write to read from that data from that device faster. So here is like the same thing. So you pay based on the use cases that you have. And another change is that back in 10 years ago, there were not a lot of people that were knowing how Hadoop works, or what is the underlying system, how we can interact with the data systems. So there was a shift in the past 5 years in the big data community to build systems like even like small businesses or normal people with the limited skills in the programming. They also can use these systems without knowing a lot of technical stuff that are happening under the hood. And the idea was that we should create like an abstraction layer on top of most of these big data systems, so that you make it easier for the people to utilize this system. Yes.
So if the technology is changing every few years and these companies are working with such huge amounts of data, how hard is it going to be for them to keep up with the latest technology, and will they realistically be able to do that?
So they are not, when you store the data in one system, so all of these changes, especially in the big data space, they are backward compatible. So meaning that you are not, obviously you have to pay the cost to move the data from one system to the new system, but you are not paying too much cost for transforming data differently. So that's the only, cost that you have to pay. The reason is that we are always trying to basically see what is the bottleneck at that period of time and trying to build a system that actually can handle that bottleneck. So 10 years ago, storage was bottleneck. So we didn't have like a fast storage. So we had to cluster different storage and then cope with like inconsistencies between the storage of speed of the different storages. And then after a couple of years, so we had like the storage wasn't bottleneck. We could basically get whatever amount of storage that we want and then cluster them together. But then the memory became cheap, which I'm going to talk about. That's why people put a lot of efforts to make that memory efficient, also in conjunction with the storage. And nowadays, so we have like a CPU is becoming a bottleneck. So it's wasting a lot of CPU cycles waiting for the data to come in. So I'll talk about it in a second. And there's a need for a scalable analytics, meaning that you don't want, if you are a small business or a small company that you are basically using any of these big data technologies to store your data for your analytics, so you don't want to pay upfront costs in advance when you don't know whether you are like scaling or not. So you wanted to be able to adopt an architecture and use a system that lets you scale up when there is a need. So, and if it's not, you can scale down, scale back, and then just pay the cost, especially if you're using a cloud system. for the amount of data processing unit that you are consuming.
So when it comes to data architecture, if I am a medium-sized business, or even if I'm a large-sized business, to what extent is the data architecture my responsibility, and to what extent is it the responsibility of the cloud service provider? Right? So where's that dividing line, and are the cloud service providers essentially starting to move into domains that used to be the domain of kind of the IT department, so that you can kind of go lean internally and then just kind of let a lot of the architecture stuff be handled by the cloud service provider?
Yeah, they are getting better, but now it's not. The cloud services right now, they are providing the building blocks. So even if you are working in a small company or a big company utilizing cloud services, you have to know at least data architectures, patterns, in order to be able to put those building blocks efficiently for the use case. So they cannot just this is not like I create this storage and then it's like one scenario that fits all use cases. So depending on the different use case, different applications, you may basically create this, construct this building block or a pipeline differently. So, and so now there's a whole suite of technologies in the big data ecosystems, especially most of them open source. And then even the commercial space, they are building off of the open source by enhancing them or taking the capabilities that they provide and then customize it for the customers. And then it's like a very big space. And then if you wanted to know which data is useful, which particular framework or the technology is useful for your company, might not be an easy thing to do. You have a tons of option for a relational databases at scale, or even new SQL or NoSQL systems, or even a graph analytics is another thing. So where wherever there is a association between two data points, you don't want it to store that inside a traditional relational table structure, because that creates some storage overhead issues where you don't need to. And then if you wanted to traverse that data in a tabular format, you have to pay the penalty of the processing that data in that specific format, where you basically represent that data in a graph format, the same data in a graph format, then you will be able to get a faster faster processing speed by just changing the representation from tabular to graph, depending on the use case. And we talked about these traditional approaches in the storage systems, where you had this system and we were saying that I'm going to think about a schema and then I decide the structure. But there's also a change in the use cases as well. So the business user, they had to in advance provide a set of questions to the data architects or the IT, saying that, hey, even if you are working in isolation, coming up with a list of questions that we may have, we also may wanted to use these set of questions, and they were providing some list of questions. And then the IT had to basically provide a structures or an architecture that enable the user to be able to answer the questions that they had. Now it's reversed. So the IT's main responsibility is create a structure that you could basically query based on whatever you want. So you're not limited by the structure that is provided by the IT and the set of questions that you provided in advance.
Now, this is interesting, because we talk all the time about how the business users need to be able to communicate with the IT folks, and the IT folks need to communicate back with the decision makers. But this model seems to suggest that the IT folks can operate almost in complete ignorance about how the data is going to be used, and that because it's going to be so flexible, if they build it sufficiently flexible, then it's sort of not their problem.
Right.
And someone else, like maybe the data scientist, will
figure it out later. Yes, exactly. So here, the blocking party was IT. So you had, as a user, you had a set of questions. You had to pass it to IT. They had to go through this series of implementation engineering to create a systems that lets you answer those questions. And during that time frame, you're basically blocked by this, this party, this division, the IT division, to be able to provide that. You wouldn't be able to do anything until they come back to you and say, hey, here's the system, go and then use it to answer your question. Whereas here, the IT says, so I'm going to integrate the data in a way that you could be able to submit whatever query do you want, but you have to do a little bit more work. So before, I would structure everything for you, and I will tell you, here is the field Y, field Z, and field X, and then here is the way that you need to interact with my system, otherwise I will not be able to answer your question. That is the standard things in the API development, where you are creating an interface with the external parties and telling them, hey, here is the contract that I'm signing with you as a user or a third party, and then in this contract I'm defining this set of fields and this set of protocol that you need to use in order to be able to interact with me. And the blocking here was that if a user wants to have a new feature or new capabilities, they had to go back to the IT saying that, hey, this is cool that you have, but I need this thing which is now is important to me. Could you provide this again? And the IT has to go back and then check all the a backward compatibility issue and all those kind of things. Then seeing that if they expose that new feature to you, whether they endanger the previous use cases or they would endanger anybody else. So at some point of time, they may come back to you and say, hey, sorry, we cannot provide that feature to you because there are some issues that we cannot handle, and the architecture backend cannot allow us to do these kind of things. And then it basically restricted the innovations or the capabilities that the user could utilize. Whereas in the new structure, they're saying that, hey, we're going to store the raw data. Let's see if this is a new. I'm going to talk about this, but they're saying that we are going to store the raw data for you, and they were going to create a data lake architecture where we pull the data from multiple resources, and then we give you an abstraction layer that lets you interact with that raw data. But you have to figure it out by yourself how you want to structure this. So in the traditional system, there is a notion we call schema on write. That means that you create a schema when you are writing the data to the storage. So that means that you are saying that, hey, I wanted this field goes to this column, this field goes to this column, and so on and so forth. And then you in advance check for validity. So if the user is storing something like a string instead of integer in a column that is integer, so you would be able to block that, right? That's called the schema on write. Whereas here we call a schema on read, meaning that you basically have access to raw data, and whenever you wanted to go and then read that data and consume and use it, you apply the schema on the fly. So, and that schema could change across applications, across use cases, and then you can define different schema based on different use cases. So you're not blocked by the predefined schema that limits the innovation and the query. Yes?
So is there a standard for the data lake architecture you mentioned?
Yeah, well, I'm going to talk about data lakes in a second. Yeah. Yes?
This really resonates with me. The first example, the traditional, because I feel like I face that constantly where IT says, oh, this extra query, this field is going to take us X many days for us to build out. It's very frustrating. So in the new approach, what's the linkage? Because companies are very complex with different systems and databases. So is there a single thread that links them all together so that you can combine sales data with inventory data, because they're all disparate systems?
Yeah, so there are solutions called for the data governance and data integration. And there are some open source solutions, like Apache Navigator is one of those. So it lets you to integrate data from multiple resources and multiple format into one place. So I'm going to touch briefly on that in later slides. So, and are you familiar with these two terms, OLTP and OLAP? So how many of you are not familiar with this?
We didn't cover this in class.
So you didn't cover it in this class. So this is stand for online transaction processing, and OLAP is online analytical processing. And in the past, so people wanted to do any of these two type of use cases. So OLTP is like a transactional processing where you wanted to, for example, you wanted to withdraw something from your bank account. That is a transaction, right? You wanted to make sure the fund is there, and then you are withdrawing the correct amount, and then until the time that you deliver the money back to the user that is correctly deducted from the account. So it's all or nothing. So there's a sequence of events that needs to be happen in one transaction, and if all of them goes through, then you're okay. If not, you just roll back and say, hey, the transaction is not valid. So, and the analytical processing, you are not basically care about the individual request or the individual transaction. You are interested in doing some aggregation or some overall analytics. So meaning that how many transactions happened last day or last week. How many transactions were like more than $1,000 or something like that. So those kind of use cases were common in the financial industry, and the people were using like one system to doing both. So, but with the growth in the data and the size and the volume of the data, so people realize that they cannot basically do those kind of OLAP type of processing by representing data or storing data in the OLTP type of system. So that's why they created systems that are completely tuned for the OLAP type of processing versus the OLTP type of processing. Or if you're doing in one code base or one ecosystem, you can switch from one to the other if you want to, if your use case allows you to do that. So talking about the OLTP, so CRUD transactions, CRUD stands for create, read, update, and delete. So these are the 4 primitive operations that you do in any database. So OLTP systems, they are tuned for the CRUD transactions, and they are tuned for frequent updates. You wanted to write, whatever transaction happens, you wanted to write to a database frequently. Whereas in the OLAP type of system, you are doing aggregation and you are mostly reading from data. You're not updating. So you are interested in knowing some historical data, or you're interested to do some aggregation. So because of these 2 differences in terms of like the updating and also the reading the data, so we are not we can relax some of the properties that comes with these systems in favor of each other. So if we are not writing a lot into a database, so why should we pay the penalty for like having a system that checks those kind of writes and make sure that they are happening? So we don't need that. So we can just get rid of that and then make the system lighter and simpler, and then at least get some like the speed in the aggregation that you want. Not sure why this is not. This is this way, but okay. So I have. Sorry. No, it is. I checked it. I don't know. Maybe it's because in this. Yeah. But this is like example query. So if you are not familiar with like a SQL, so this is example SQL query where you're saying that I wanted to, like here you were saying that I wanted to select from this table. So the last transaction, for example, right? But here, for the OLAP type of query, you're saying that I wanted to select particular fields from this 2 tables, and I wanted to calculate the sum over a period of time of the transactions or the amount of data that are basically updated into this database. So I talked about the data warehouse where you had the different databases inside like a company. Even in different locations, you had to create a system, the ETL systems, extract load transform systems, use those kind of like systems which allow you to basically cleaning the data, they integrate the data the way that you want, and then put that inside the data warehouse based on the schema, and then you make it available to the users. When you go through this ETL process, like we talked about, this could be also applied to different like a type of applications, not just like a different storage of the same type or same application. It could be data that are coming from different systems. So you pull the data from like the operational system, you pull the data from ERP system, or even like a flat files or the raw data that comes out of the sensors, and then you apply that ETL process in order to extract only the columns or the fields or the data points that you require for your analysis.
So,
right?
So the key thing here is this is not about the location of the data.
Yeah.
Right? You can have a data warehouse in the cloud, and you can also have a data lake
in the cloud. Yeah.
You can have a data warehouse on-premise, right, in your servers. You can have a data lake
on-premise, exactly.
In your servers.
Yeah.
But the data warehouse concept is something which, even though people are saying that we're moving away from that to the data lake, there are some organizations and functions that for which the data warehouse is optimized, right? Like financial institutions, they claim that they will never move to a data lake for at least transaction data.
Right, because they require these CRUD tasks. So you want it to be able to do create, read, and update, and delete in an atomic way. So if we like in the terms of in the example that I gave for the transaction, so there's a series of operations that needs to be done all at once. So you cannot say, hey, I don't care like if I get the response from this machine 10 milliseconds later. So whereas in the modern system, if you are writing a review in Amazon, right? So Amazon can show you like the top 10 or 20 reviews. If somebody is writing a review at the same time, so they can just capture that review or store that review and show it to you like a couple of seconds later, or show it to a new user, not you, because you don't lose that much, right? So by not just looking at the review at the same time, that is generated at the same time as you are seeing the product. Whereas in the financial industry, if somebody at the same time wants to withdraw money from that account, and then you're also going to basically withdrawing money from the same account, there should be some like a mechanism that put these two in order, or make sure that one happens before the other to avoid the inconsistency for those operations. Yes?
So in the Amazon example you gave, like where he's given the review while somebody else is reading the review, that's the lake scenario?
Yeah, that's what we call the eventual consistency. So in the transactional system, everything should be consistent at the time that they are happening. So if the review is written right now, everybody that is using that system should be able to see that review exactly when it's written to the system. So that's like a one view across the whole system. Whereas in the eventual consistency, it means that at some point in the time, later in the time, the system will be consistent. And then the later users should be able to see the status of the systems at some point of time. Yes?
So the previous slide, OLAP and so one of them is eventual consistency. Which one is given? OLAP is eventual consistency.
It's not dependent on this. So depending on the systems, you could have both OLTP and OLAP in the consistent system and the transactional systems, and you could also have both of them in the eventual consistency, in the big data domain. So in terms of the transaction, if you are doing it like writing a review, if you look at it as a transaction, so you're saying that like a transaction should happen if all the steps that I defined for a transaction are completed, right? And at least I have some like information about the validity of those steps. But in big data system, the Amazon example that I gave, you could say, if this doesn't happen, I don't want it to block the user from accessing the reviews. I wanted to show the user some status of the system up to some point of time that I can provide that status. And then if the user comes back again in 5 seconds later, I would be able to show that again, the newest status. Yes?
So in the ETL, I'm not sure if you're going to cover this later, but it seems like a pretty critical task to bring together all that data. How do companies usually handle it? Do they outsource it or build their own?
So it varies. So this is not an easy task, by the way. So they have to go through the process of understanding all the resources, and then brainstorm about the structure, how the structure should be created, that basically maximize the use cases that the company is trying to address. And if they cannot basically create that structure in the data warehouse as efficient as possible, they go through this whole cycle and loop of transformation after transformation for different use cases. So some companies, they outsource it to big companies, some they just like do it themselves, and then they just buy this hassle of transforming the data. Yeah. So whereas in the data lake, I talked about this, you put all the data, regardless of their types or the source that they are coming, into one place. And these are all raw data. They are not like schematized. They are not structured in a one way or the other, in a particular format. You dump all of them into one place, and then you tell the user, hey, if you wanted to use like a web logs and email logs, so they are in this file or in this storage, you could go and then just sneak there and then see what is the structure and then transform the structure based on your use case. And if another user or another data scientist comes back again that wants to use the same data differently, they don't have to go through the series of transformation again, so they can just use the raw data the way they want. So the key points for the data lakes is you store all the data, like I said, you transform as needed, and apply the schema as needed. And then we have like a traditional stack where you store the data inside your data lake, and then you use different like systems for different layers, as you see in the stack, in order to do ETL processing on the fly, if you will. So the data is stored inside the data lake. We have like a systems that lets you apply a schema on the fly, like Avro, Thrift, and Protobuf. Protobuf is for the Google. So lets you create that schema also on the data that's sitting on the data storage. And this is a binary schema, binary file format where, you know, the traditional, if you are familiar with the HTML file or a JSON file or an XML file, these are like a human readable formats. Yes?
So if I understand this right, the query is going to be consistent across all different formats. So the underlying processing for the query will take care of whatever format it is.
Yeah, so when you are basically storing the data here, so you don't have to change anything in the upper layers. So the data is stored in a raw format, and then when you expose that data through this schematization process to any of these formats, then all the other applications that can interact with that the way they would with the traditional data warehouse. So if you have if you write a query here, over here, a SQL query that extracts the data from like a warehouse, you could basically run the same query on top of the data that's sitting on the data lake. Yes. So, okay. These are like the differences between the data warehouse and data lake. Some of the differences, not all of them. So you go from the, predefined schema to like the schema on demand. You go from like just keeping part of the data. In the data warehouse systems, when you go through the ETL process, because of some storage requirement or storage restrictions, you are not going to store the raw data, right? You're going to filter that data based on the schema that you come up with. And sometimes companies are getting rid of like some of the raw data, thinking of, hey, we're not going to use, like, for example, geolocation of users. So we are only interested in about the user interactions and some other statistics. So we're going to get rid of that. But later on, if they wanted to use that geolocation, they have to go back and see whether they can get, first of all, they can get the raw data again, and then go through the series of transformation to extract that data points for their use case. Whereas in the data lake format, you're saying that we're going to store all the data. We're not losing anything. We're not deleting or basically destroying anything, because at some point later time we may want to use that all of the data. So, and then we are going to transform the data on demand and then apply the schema as needed. But there is a trade-off here when you go to the data lake versus data warehouse system. It's just like a quick response time. If you know in advance what is the structure and then how the data is defined and is schematized, you can just write a query and that basically goes and basically extract the data from the columns and from the schema that you define. Whereas
even in the data lake context where everything's just dumped in there,
right,
without a schema, you still have to think about kind of tagging the data, right? So, for instance, if I want to match up, tweets with purchasing behavior with geolocation data, right? It's going to be impossible to connect these different types of data to make a reasonable query if it hasn't been coded on the way in with the kind of the relevant tags.
So typically there is no like a tag or a schema attached to a raw data in a sense that you could go and look at that. What typically data scientists or data architecture do is they look at, they get a sample of the data, raw data, and look at the format and then see, based on the format that the raw data has, how basically they have to transform that data on the fly to be able to expose that data in their application for the application. So there is like a data wrangling or data like exploration phase in between that you have to go through when it comes to working with a data lake. Whereas here, we're giving you a contract. So this is a table, this is a structure. So you know in advance, you don't need to have to go and then look at the data in the data warehouse. So whereas there, you need to go and then look at the data. Now I'm going to talk about the elements of the data analytics inside, and then the effects in the data architecture. So we start typically in any analytics pipeline, we start by systems that collect and ingest the data to the system. So this could be collecting data that are sitting at rest, or getting a data sets, large files that are basically available publicly or that are shared with the company, and also getting a data from a streaming resource like Twitter, Firehose, or Wikimedia, those kind of things that are generating data pretty fast. And then you store the raw data. This is like a traditional pipeline. You store that, store the raw data. You clean and transform the data on demand, and then you expose them through to different layers. Like either you basically submit a query to your system after data is cleaned, or you do some aggregation. This is like an OLTP type and OLAP. Those are done into two different layers. And then you basically expose that results to the user as like a serving layer. Yes?
Would streaming telemetry also follow the same process?
Streaming analytics?
Yeah.
Yes, it goes through the same, but you don't store anything here. So you just have to remove the storage right from here, and then you have the streaming pipeline. So data comes in, processed, the report is created, and this data is going to be served to the application and the user. So we're going from this, typical high-level architecture. I'm going to map this with the current technology or the common big data technologies that people use in order to implement such a pipeline. I guess I got a question how you could basically do this. So, one of the common system for data ingestion or data collection is Kafka, which is built on LinkedIn. So they had this problem of basically communicating or extracting data from multiple resources, and then they had to pay a penalty of transforming the data and then come up with some ad hoc systems that can talk to different systems differently. So and then they realized that this is not an efficient way as they were scaling out. So they created a system that lets them to store the data and then scale out as needed as you grow. So and then you only come back to this system in order to read the data as you want to. So if there is like a news feed, the application, it generates something, it puts that data inside this Kafka queues, and then whatever application that requires that data goes and then reads off of this. And then one interesting thing here is that in the collection and ingestion, it's not just one input. It could be like some, you get the data from some sources, and then you make it available through this pipeline, and then you can also make the output available again through this ingestion and data source for different applications. So it's kind of like a feedback. You can also go back and then put the data again, ingest for different processing. And HDFS, you could create like a data lake with Hadoop. So HDFS stands for Hadoop File System. And then for the basically cleaning and transforming the data that sits on top of Hadoop, you use a system called Pig and Hive. So the difference is a Pig is you can write MapReduce job, and Hive is basically you can write your SQL queries, which is like a high-level abstraction. And then it translates those to the MapReduce jobs that's going to be applied on the data sitting on the HDFS. And if you wanted to do query data, you use HiveQL or Hive in order to do both OLTP and OLAP on the top of data that sits on the HDFS, and then you use like NoSQL or columnar data stores in order to serve the data. So in the relational world, if you wanted to implement such a thing with the addition of like you have to like do this kind of like a storage on the data warehouse, you use like some SQL loader or Oracle business warehouse type of tools in order to store the data inside the relational database. It could be Oracle or SQL Server. And then you use SQL in order to interact with the data both for the OLAP and OLTP. And then you store like into some data store, yes.
So how sticky are the different frameworks and technologies, right? So we all know that if you're using Oracle, you're kind of stuck with Oracle, and it's very difficult to extract yourself from Oracle and start using a different vendor. In kind of the data lake world, you're relying on open source technologies, but there's all this new stuff that keeps being developed. So Kafka didn't exist, right, 10 years ago. I mean, Hive didn't exist 10 years ago. Pig wasn't around. And so when these new things come along, how easy is it to start adapting them? Are those technologies also backward compatible typically, or are you pretty much locked into some trajectory in this data lake world? That's a really good question. So in a sense, like a data lock-in is an issue. It was an issue like 6 years ago. So where you choosing a system and then you lock yourself to that system, and you have to pay a huge penalty in order to go out of those systems. But now, in the last couple of years, we have like a maturity in the big data pipeline where we know that where you're going to put your data in HDFS, Hadoop, or even a Spark, which I'm going to talk in a little bit. And then we created like some APIs or interaction endpoints between the systems. So even if you wanted to use a new system that comes into place, there is a connector that comes with that system that you can use in order to connect your system easily with the previous systems. So there's in the open source community, especially for the big data architectures, is like we have to be both backward compatible and also have been able to expose a connector to the at least most common tools like Hadoop or Spark or Hive or those kind of things. Yeah, right. An example is that Facebook, they basically create a system called Presto for SQL, for database processing at a large scale, and they store everything on Presto. And now they're using Spark for like processing like 100 terabyte of data per day. So, but they are pulling the data from Presto to Spark very easily. So they just created like use the connector that comes with a Spark that you can connect it with Presto, and then boom, you're having the logical view on top of data that's sitting on the underlying system. The notion, especially when it comes to storage, is that we're going to be dumb about the underlying system. So then we talk with the connector, and the connector is doing the optimization or their translation of the R request to the underlying engine. Okay, so I guess I covered most of these things in a traditional business warehouse. So you pull all data into your data lake system, data warehouse system. But one other problem with the data warehouse was you had to basically, if you wanted to create a raw data, you have to also create a separate storage for the summary of that data or the transform data if you don't want to get rid of the raw data. And then you always have to keep all of these things up to date. So you have to make sure that whatever records, for example, is written to the raw data, then that's going to be transformed properly to the table or to the database that shows the summary of data. And also you have to populate the metadata as well. Whereas in the data lake form, because you're only storing the raw data and everybody applying the schema as they need to, so you always provide a consistent view of the system to the user that are utilizing that architecture. So I'm going to briefly talk about the two architecture, a big data architecture that are commonly used by many companies, including Google, Facebook, Twitter. So one is called the Lambda architecture, which is basically saying, which is an architecture that combines two different use cases together. So I gave you an example for fraud analytics where you wanted to do some sort of historical analysis, going through like a terabyte or zettabyte of data that was gathered, like for example, like for a couple of years. And then based on that, you generate some insight, and then you wanted to merge that insight with the real-time view of data. So this is a typical architecture. The way that the people construct the system is, you get the data from the incoming source, you replicate the data to two different layers, meaning the batch layers that does the batch processing stuff, and also the speed layer that does the streaming processing. And then, each of these layers, they generate their own view
based on the data inputs. So the batch data gets the new data, combines it with the historical data, and creates some batch view based on the new addition to the data. And then the streaming view speed layer also creates the a real-time view of the system based on the defined window. You could say, so this layer only shows the status of the system within the last 5 seconds or so, or 10 seconds or so.
So like with a recommendation engine, right? The batch layer, all that collaborative filtering and stuff is
Exactly,
very computationally intensive.
You push it here.
You don't need to do that in real time.
Exactly.
I know your identity. Overnight, I'm thinking about you and thinking about what to recommend for you. But then when I log on and I start moving the mouse around and start dipping in over here and dipping over there, there are certain things that I can respond to, but the whole nearest neighbor collaborative filtering algorithm, that's not really going to, the results of that are not really going to change very much based on what I've done in the last 5 seconds.
Right. Yeah, those are static analysis. So you could basically, get the batch view of a system about the past of the user, and then the reason that you replicate that data point is that over time, in a month, that may have effect on the status of the user. So the things that you were interested in 6 months ago might not be the things that you're interested in now. So these data points basically filtering these insights that are generated in a batch layer. Whereas this speed layer, it creates on the fly a view of the recommendation, if you will. Amazon uses this, and they're also creating this, exposing a service called Lambda architecture on their AWS if you wanted to utilize or create an architecture typical like this, where they basically, have you, maybe you've talked about this, that, do you know that why you're receiving some of the Amazon items even in a day, or even if you're not a Prime user, in a day, or
predictive delivery, right?
It's predictive delivery, but do you know how they do it?
With this, I'm guessing.
So they're using the same Lambda architecture, and then so they create a profile of this stuff like that in the region, and then you are also assigned to that region, and then the batch layer generates a list of items that are going to be bought by the people in this geolocation. And then so they're going to be shipped before even you place the order, right? And then so they come to the regional warehouses, and then they are sitting on the shelf for you to be ordered. And the moment that a user buys those kind of things to the that are generated through the batch view, so that is also get translated back again to the system, giving some higher weight to those kind of things. So, but there is one problem with this is that for any of these two layers, you have to use two different systems. And sometimes, this has been created 6-7 years ago, and it has been adopted by many companies, and they are still using this. But they realize that as they scale out, that maintaining two different code bases, especially for the debugging purposes, and also having ability to merge this, the result of these two systems in a good way, so that they can come with the real-time view pretty fast. Also, the batch view pretty fast is not an easy thing to do. That's why there's a new. Oh, let me just see. I'll talk about this later. There's a new architecture called Kappa architecture. So this should be Kappa, not Lambda. So the Kappa architecture assumes that all the data is inside a data lake. And, oh yeah, so sorry, but let me just, yeah, it is correct. So let me just tell you for this Lambda architecture, what you need, what are the systems that you can use in order to implement that Lambda architecture in the open source community. So for the ingestion part, you use Kafka. For the batch layer, you use Hadoop. And then for the streaming speed layer, you could use a system called Storm or Spark Streaming. And then for the serving, you could use Cassandra or whatever key value store database that are out there. You can choose that based on your use case. And this is a CAP architecture which says that, why do we need to store the data into two different systems? Essentially, you can store the data into one system, and if you wanted to do batch, you just rewind the index to the 0 point in time where you started storing the data, right? So think of it as like a queue where you store the data inside that queue, and then you have indices from where the queue begins and then where the queue ends, and then you append the data at the end of that queue. And if you want to do batch, you go and start from the beginning of that queue, start anything that you have stored up to this exact point of time that you're interested in. And if you wanted to do a streaming processing, you only go to the pointer at the end of the queue and start processing the last record inside the queue. So this makes things a little bit easier for basically doing both batch processing and streaming processing. And you could use like Kafka for that ingestion layer. You could use Storm or Spark Streaming or Hadoop for that stream processing systems. And for the serving DB, again, like Lambda, you could use Cassandra, MongoDB, or any NoSQL CouchDB that you wanted to use. So there is this new architecture called, Netflix is using this architecture, saying that, okay, so I'm going to store everything on cloud. And so I'm not going to, run my own data center. So before Netflix moves to completely to cloud, so they were having their own data center. They were storing all the movies and all those kind of things, and they had to serve that to the user. So they had the problem of scaling out as the number of user grows, and then they had to basically change the systems and maintain the big data architectures the way that the system changed. So they were saying that, hey, so if you wanted to compare the OLTP type of system with the OLAP type of systems, where in the OLTP type of system you were basically doing a lot of writes, and then in the OLAP system you were doing a lot of read. So they were saying that so most of our stuff is read. We're not writing anything, right? We're storing movies, and then people are reading those movies in order to play back that. So why do we should basically spend a lot of money in order to create like that data center and then make it tunable for this kind of analytics, whereas we can use cheap storage. So we don't have to buy a bunch of servers, create data lake using Hadoop or Spark or any other tools. So we can use cheap storage like S3, simple storage service that's provided by Amazon, and then we can store all the data, all the movies on S3, and then we let the cloud to basically run that, and then we use our tools in order to do analytics on top of the data that sits inside the cloud. So and now they're running the whole Netflix basically infrastructure off of Amazon. So there's nothing outside Amazon. Everything is on AWS services for the Netflix, and they are basically save a ton of money in upfront costs and maintaining all this, like the ecosystem of the tools that they have to maintain, and then they scale out the storage as they need to. Okay.
So maybe we can. I think we need to wrap up on this piece. So I'm wondering. I think a lot of the questions that people have about data architects is this class is focused mainly on the data scientists. As managers, what do you have to think about with respect to data architecture? Typically not, managers typically don't interact with them unless they're kind of CIOs or CTOs. But if you're making investments in data collection and data retrieval and data analytics, ultimately, you need to have good data architects.
Right. Exactly.
And so how do decision makers know whether their data architecture team really knows what they're doing, right? I mean, that's one of the biggest problems of being a generalist, and everybody here is a generalist,
right, is
that these people are experts. They know more about it than you do, and so they can tell you things that aren't true as a way of kind of making themselves indispensable or keeping their jobs and so forth. Mm-hmm. So how do you evaluate whether a data architecture team is really up to snuff, really is good, they really know what they're doing? Will the data scientists be able to tell you? Will they know? Or
data scientists could help. So the low bar here is that if you always have in mind like a data lake and data warehouse, where if there is like a good architecture in place, so if you wanted to create a new use case, you shouldn't go through the hassle of like a months or like even weeks in order to make that make the data available for the new use case. So the architecture should be flexible, scalable, and be up and running less than a couple of days for the new use case, if the underlying data architecture is designed and built correctly.
So a good kind of metric or kind of KPI for your...
Change the use case and see how long does it take
Yeah.
for that use case to be implemented. If it's in a matter of like a day, great. So it is basically done correctly at least. And then if you are providing a complex use case and it takes even like months in order to be delivered, so that you are seeing that they have to go through the series of transformation to create that data for you or for the new use case. Yeah. Okay.
How can companies who build software and services on top of open source technology, like Hortonworks or Databricks, help kind of democratize data for business people to make it accessible to them and make it easier for them to get it? Because even at that layer, it's still pretty challenging for a business person to go in and dive into it. So how can they help bridge that gap?
Yeah, so they're not, these two companies that you mentioned, they're not capturing any data. So they're not storing any data, they're providing services. So the Databricks, they provide the Spark services. So what they are trying to do right now is creating abstraction layer as much as possible, easy enough for the people to be able to use those high-end systems. So if you had to basically implement a stack like this, that would take like a couple of months to implement. Nowadays, you should be able to have a stack like this in a couple of weeks. So and then we are, they're working in basically shortening those time, less and less and less. So in the past, you had to write a program in order to interact with Hadoop. So and then there were not a lot of people that were able to write a Java program complex enough to work with Hadoop. That's why people create like a whole suite of technology on top of that. Yeah.
And just to build on that though, do you think that a basic skill for business managers today should be SQL?
Yeah.
If I just changed jobs, I don't know SQL, and I need to learn it by yesterday.
Yeah. So the more the SQL.
There's a good stamp
yeah.
book for that.
Yeah. So SQL is a standard query language, and then since a lot of people know, at least in the data science community and the data analysts, they are knowing that.
Yeah.
We are going toward that direction, assuming that a SQL is like English.
Yeah.
That if you wanted to travel from one country to another country, you should know this, or at least a common language. And then that would be a common language that different systems are going to be tied back together. So if at some point as a manager you wanted to be able to do what's happening in the system, rather than picking up the phone and calling the IT, hey, could you tell me how many users bought this particular item in the past 6 days? You should be able to write a simple query, one line on the system and get the response pretty fast.
So are there any
I
other
recommend.
languages in addition to SQL that are coming our way that we need to learn?
Yeah, so there are machine learning, not in the advanced form, but in a sense of yeah, I guess. No, you shouldn't learn. No, I wasn't saying that you should learn machine learning. I was saying that there are different type of algorithms. You should at least know what the differences are. So what I'm saying is that if you are writing a SQL query and you're not getting a response, then if you wanted to get some prediction capability out of a system, so you should be able to ask the right question in the first place. Otherwise, you basically delegate that to a data scientist or someone else to figure out what would be the right terminology. At least if you know at the very, very high level what is the difference between A and B, and then how you can basically use them, or what are the scenarios that you apply, at least you can have a better conversation with the data scientist or the IT to guide them, hey. Or they can at least tell you at the very high level, hey, here is we're just clustering some data points on average, or we're trying to create some system that predicts everything based on the individual user. not based on average. Simple as that, right?
Thank you.
You're welcome. Yes.
Sorry, one more. So you said you work on Spark. So using Spark SQL isn't completely trivial. So to touch on your point, are there like plans to add another kind of layer of abstraction
Yeah.
to really simplify the data access?
Right, so 2.1 is the latest version of Spark, and in this version, so there was a very huge improvement in the Spark SQL to make it easier and match with the what's the standard for the SQL 2003. So now you should be able to use like Spark SQL very similar to how you were using SQL to interact with any relational database in a year or two. Yes.
Should there be any considerations about compression of data? It just seems like so much of this, like on that Boeing flight,
Right.
I don't see what takes up so much data on just a 1 hour flight. It's like
Yeah, so there's those are the sensors that are basically that were basically built by different manufacturers, and then they put them here, and then they are generating the data that should be compliant with some regulation and standards. They cannot just like, hey, I'm going to compress this data and then with my own format, and then somebody else wants to dig into that data for if a crash happens or something. So they have to go through those stuff, but but when you wanted to transfer that data or start processing that data, you could compress that. That's why these technologies, under the hood, they always take advantage of compression. So when you wanted to store the data in Hadoop, it's not stored in the raw format. It's compressed using a different, compression algorithms like Snappy or gzip or those kind of things. And then now, even in Spark, in a new modern big data system, we are moving toward the capability of being able to apply query on the compressed data. And right now, you could do this on a Spark. There's a package called Succinct, which lets you compress the data and do some simple query on top of the compressed data. So and then, so that is something that we are going to see in a couple of years to come. So all data is compressed. You will be able to do a query on compressed data.
So businesses don't need to really think about this at all.
Yeah, no, it's been taken care of. So the goal here is that, these systems are going to create like abstraction layer for you to use it, and the underlying systems is going to be more intelligent to basically optimize the plan, come up with a best way of representing or storing that data.
So one of the early founders of Facebook, or investors of Facebook, said that the goal of a modern corporation is to let everyone within the company, every decision maker, so-called party on the data, right? I mean, he was like 23 or whatever when he was a co-founder. He said, party on the data, which means get rid of all these middlemen and all of these people and all these opaque processes that stand between the decision maker and the technology. And so I think what you're describing is a way of kind of surfacing the data in ways that the managers can kind of make sense of it.
Right, exactly.
Yeah.
Yeah.
Well, thank you, Arash.
You're welcome.
We've got another. You probably already have one of these, but you can.
Oh, thank you.
You never have too many of these.
Yeah. Yeah, thank you.
So, thanks for coming in.
You're welcome.
We're going to take just a quick stretch break, and then we'll wrap up and get out of here. So, I want to grab Arash real quick.